Take a deep breath, allowing your shoulders to drop and your body to find its natural center of gravity against the surface beneath you. As you exhale, let the tension of the day dissolve into the quiet air around you, leaving you open to the vast, silent wonders of the chemical cosmos. You might imagine that the vacuum of space is a sterile, odorless void, but the universe is actually a rich, aromatic tapestry, woven from the very elements that make up your own body. Within the first few moments of an astronaut returning from a spacewalk and re-entering the airlock as the pressure equalizes, they are often met with a distinct and startling aroma. This smell of space is frequently described as a metallic sensation, similar to the scent of seared steak, hot metal, or even the bitter fumes of welding. This isn't just a trick of the mind. It is the result of high-energy particles, ionizing radiation, vibrating the oxygen molecules within the spacecraft, creating a trace amount of ozone, or O3. This sharp, ozone-rich scent is your first tactile connection to the high-energy environment of the stars, a reminder that even the emptiness of the void has a physical, sensory presence. Consider the moon, that silver orb hanging in our night sky. When the Apollo astronauts, starting with Neil Armstrong and Buzz Aldrin in 1969, tracked lunar dust back into the lunar module, they were surprised by its potent olfactory signature. They described the scent of the lunar regolith as remarkably similar to spent gunpowder or the smell in the air after a firecracker has gone off. This is a scientific curiosity because the moon contains no oxygen or sulfur to create a combustion-based smell. Instead, researchers believe this gunpowder aroma is the result of the desert glass created by meteorite impacts, combined with the chemical reactions of solar wind particles trapped within the dust for billions of years. As you drift deeper into relaxation, imagine running your hand through that soft, charcoal-gray dust, feeling its abrasive texture, a texture caused by the lack of wind or water to erode the sharp edges of the silicate grains. It is a dry, ancient scent, the smell of a world that has remained unchanged for over 4 billion years. As we move further away from our home planet, we travel 26,000 light-years toward the very heart of our galaxy, the Milky Way. Here, within the massive swirling molecular cloud known as Sagittarius B2, the universe reveals a surprisingly sweet secret. This cloud contains a staggering volume of ethyl formate, a chemical compound with the formula C3H6O2. In a laboratory on Earth, this is the very same molecule that gives raspberries their signature tartness and contributes to the distinct aroma of Caribbean rum. Imagine the sheer scale of this, a cloud of gas and dust spanning trillions of miles, saturated with the essence of a summer fruit. Sagittarius B2 is estimated to contain 10 billion liters of alcohol, a cosmic distillery floating in the freezing darkness. It is a comforting thought that the building blocks of the things we find delicious and soothing on Earth are manufactured in the intense pressures and cold temperatures of deep space molecular clouds, which typically hover around a frigid 10 to 30 Kelvin. The sense of smell is unique among our human perceptions. While sight and sound are processed through the thalamus, the brain's relay station, the olfactory bulb has a direct, unmediated line to the amygdala and the hippocampus. These are the regions of your brain responsible for emotion and memory. This is why a single scent can instantly transport you back to a specific moment in your childhood. In the same way, the molecules drifting through the cosmos are the memory of the universe. Consider the polycyclic aromatic hydrocarbons, or PAHs. These are complex organic molecules that look like chicken wire, made of carbon and hydrogen. Scientists estimate that PAHs carry more than 20% of all the carbon in the universe. On Earth, you know their scent well. They are the char on a grilled piece of toast, or the earthy, smoky aroma of a forest fire. In the deep reaches of space, these molecules are produced by dying stars, ejected into the void to become the seeds for new solar systems. You are quite literally made of this smoky ancient stardust, and the very air you breathe is recycled through these epic billion-year cycles of stellar life and death. If we were to visit the giant planets of our outer solar system, the olfactory experience would change dramatically. Uranus, for instance, has an upper atmosphere dominated by hydrogen sulfide, the same molecule, H2S, that gives rotten eggs their pungent odor. This was confirmed by spectroscopic measurements in 2018, which identified the signature of these molecules at the 1 bar pressure level of the planet's cloud tops. While this might seem unpleasant in the context of the vast cold gas giant, it is simply a chemical signature of its evolution, a dense, sulfurous veil hanging over a world where the surface is a slushy ocean of water, ammonia, and methane ice. The pressure here is so intense that it could squeeze carbon into diamonds, which then rain down through the atmosphere like crystalline hail. Imagine the sound of that diamond rain, a soft rhythmic tapping against a metallic hull, a white noise symphony of falling gems. Nearer to the sun, we encounter the moon Io, one of Jupiter's most fascinating satellites. Io is the most volcanically active body in our solar system, with over 400 active volcanoes constantly resurfacing the moon with sulfur and sulfur dioxide. The scent here would be sharp and acrid, like a freshly struck match. This sulfur dioxide, SO2, creates a thin, tenuous atmosphere that constantly freezes and thaws as Io moves in and out of Jupiter's massive shadow. The temperature can swing from -202 degrees Fahrenheit to thousands of degrees near the volcanic vents. Feel the contrast in your mind, the biting cold of the vacuum and the radiating warmth of the molten rock. It is a world of extreme temperatures, yet it follows a predictable rhythmic orbit, locked in a gravitational dance with Jupiter and the other Galilean moons, Europa and Ganymede. In 2014, the Rosetta mission reached comet 67P/Churyumov-Gerasimenko and used an instrument called Rosina to sniff the comet's coma. The results were a complex cocktail of chemicals. The comet smelled of ammonia, like a strong cleaning fluid, formaldehyde, a sharp, pickling scent, and hydrogen cyanide, which carries the bitter, dry aroma of almonds. This chemical fingerprint is a time capsule. Comets are the dirty snowballs of the universe, preserving the original chemistry of the solar nebula from 4.6 billion years ago. When you think of a comet, do not think of it as a terrifying streak across the sky, but as a gentle, frozen messenger carrying the ancient perfumes of our origins. The methanol, or wood alcohol, found on 67P is a precursor to the complex organic molecules that eventually led to life on Earth. As you settle deeper into your rest, consider the scent of a planet closer to home. Mars. The red planet is a world of iron oxide, the very same compound, Fe2O3, that creates rust on Earth. Because of this, the Martian dust has a dry, metallic, slightly chalky scent. In 2004, the Spirit and Opportunity rovers discovered that this dust is incredibly fine, like talcum powder, and it clings to everything because of static electricity. Imagine a soft, rust-colored wind blowing across the Gusev crater. The sound, a low, mournful whistle. There is no moisture to carry the scent of petrichor, that wonderful earthy smell of rain on dry soil, because the atmospheric pressure on Mars is less than 1% of Earth's. But there is a quiet beauty in the stillness of the Martian plains, where the sun appears blue as it sets behind the dust-filled horizon. Even the most distant reaches of the Orion Nebula, a massive nursery where stars are currently being born, have been found to contain formaldehyde and methanol. Using telescopes as extraterrestrial noses, astronomers use spectroscopy to break down light into its component colors, revealing the unique barcodes of these molecules. We know that the Orion Nebula is 1,344 light-years away, yet we can identify the specific vibration of a carbon atom bonding with an oxygen atom within it. This connectivity is a fundamental truth of our existence. The same chemistry that creates the scent of a pine forest or the aroma of fresh morning air is at work in the pillars of creation and the heart of the Andromeda Galaxy. Think of the sheer age of these molecules. Some of the organic compounds detected in meteorites that have fallen to Earth are older than the Sun itself. They have traveled through the interstellar medium for billions of years, surviving the intense ultraviolet radiation of young stars and the shock waves of supernova. When you catch a familiar scent, perhaps the smell of old paper, a specific spice, or the air just before a thunderstorm, you are participating in a tradition of chemical recognition that spans the history of the universe. The comfort of a familiar scent is not just a psychological quirk, it is a biological anchor. The scent of vanilla, for example, contains vanillin, a molecule that has been detected in the residue of ancient celestial events. The universe is not a cold, indifferent machine. It is a fragrant, textured, and deeply connected system. In the microscopic world, molecules are constantly vibrating, even at temperatures near absolute zero. This vibration is a form of music, a silent hum that permeates every atom of your being. As you drift closer to sleep, imagine you are floating in a cloud of ethyl formaldehyde, surrounded by the soft, sweet scent of raspberries and the gentle glow of distant stars. The pressure of the universe is a comforting embrace, a reminder that you are never truly alone in the void. You are a part of the architecture, a collection of these very same molecules, arranged in a miraculous thinking form. In the next part of our journey, we will descend further into the microscopic mechanics of these scents, exploring how a single molecule can travel across the vacuum of space to tell a story of a star's birth. But for now, let the metallic tang of the airlock, the gunpowder dust of the moon, and the raspberry heart of the galaxy lull you into a state of profound peace. The cosmos is vast, but it is familiar. It is made of the same stuff as your dreams. Feel the weightlessness of your limbs, the slow, rhythmic pace of your breath, and the cooling temperature of the air around you. The stars are watching over the slow chemical dance of your rest. You are safe. You are home. You are part of the infinite aromatic mystery of the dark. Imagine the velvet dark of a 19th century laboratory, where the air is cool and the only light comes from a slender beam of sun passing through a glass prism. In 1814, a German optician named Joseph von Fraunhofer peered into this rainbow of light and noticed something curious: hundreds of tiny dark lines cutting through the colors. He meticulously mapped 574 of these lines, unaware that he was looking at the universe's own olfactory signature. These dark bands, which we now call Fraunhofer lines, are the shadows cast by specific atoms and molecules absorbing light. Just as a certain scent can trigger a memory, these lines allow us to smell the composition of a star from trillions of miles away. As you settle into the stillness of your room, permit your mind to visualize these dark lines as the barcodes of the cosmos, the silent indicators of hydrogen, helium, and the complex organic molecules that fill the boundless theater of space. Long before we had the technology to launch probes into the void, humans were already connected to the chemistry of the stars through the rare gifts that fell from the sky. On the morning of September 28, 1969, a massive meteorite streaked across the sky over Victoria, Australia, breaking into fragments near the town of Murchison. When residents approached the impact sites, they were met with a powerful, unmistakable odor, the sharp, cold scent of methylated spirits and wood alcohol. This was the Murchison meteorite, a carbonaceous chondrite that is approximately 4.5 billion years old, older than the Earth itself. Scientists later discovered that this stone was packed with over 70 different amino acids, the basic units of proteins. It was a historical turning point. For the first time, we had physical proof that the building blocks of life and the scents associated with them were being manufactured in the cold, pressurized depths of space long before our solar system even existed. Yield to the heavy embrace of your bed, feeling the steady pull of gravity that keeps us anchored while our understanding reaches toward the stars. While we often think of our sense of smell as a modern luxury, it is actually our most ancient survival tool. Humans possess approximately 10 million olfactory receptors in the nose, categorized into about 400 distinct types. This biological hardware has evolved over millions of years to detect molecules in incredibly small concentrations. For instance, the human nose is sensitive enough to detect geosmin, the chemical responsible for the scent of rain on dry earth, at a concentration of just 5 parts per trillion. This hypersensitivity exists because, for our ancestors, the scent of water meant life. In the same way, the chemicals we detect in the interstellar medium, like the formaldehyde discovered in 1970 using the 140-foot Green Bank telescope, are the cosmic precursors to the water and air that sustain us now. As we look further back into the history of our cosmic neighborhood, we find the work of the Cassini-Huygens mission, which began its exploration of the Saturnian system in 2004. One of its most striking discoveries was the atmosphere of Titan, Saturn's largest moon. Titan is a world of orange haze and frozen rivers of liquid methane, but its chemistry is hauntingly familiar. The mission's visual and infrared mapping spectrometer, VIMS, detected the presence of benzaldehyde in the moon's upper atmosphere. On Earth, benzaldehyde is the primary component of bitter almond oil and gives cherries their distinct, sweet aroma. Consider the quiet, rhythmic rotation of Titan, a world where the air smells of almonds and the temperature sits at a stable, frozen 94 Kelvin. It is a slow-motion world of heavy, nitrogen-rich air, where the wind moves at a mere few meters per second, a gentle stirring in a giant, cherry-scented freezer. Within the artificial environments we have built to reach these heights, such as the International Space Station, the olfactory landscape is equally fascinating. The ISS has a unique interior scent that astronauts describe as a mix of ozone, hot metal, and the faint plastic aroma of phthalates, chemicals used to make plastics flexible. Because the station is a closed system with a total pressurized volume of about 32,333 cubic feet, every molecule is recycled. The environmental control and life support systems must constantly filter out metabolic waste and the off-gassing from electronics. In 1976, when the Viking 1 lander touched down on Mars, it carried a gas chromatograph mass spectrometer, GCMS, designed to sniff the Martian soil for organic molecules. Though it heated the soil to 350 degrees Celsius, it found a world that was chemically clean to the point of being sterile. This historical discovery changed our view of the red planet, shifting it from a place of potential lushness to a dry, oxidized desert where the air is 95% carbon dioxide. Invite a sense of calm as you contemplate the rhythmic nature of these molecular cycles. In the deep reaches of a molecular cloud, the density is incredibly low, ranging from 100 to 1 million particles per cubic centimeter. For comparison, the air you are breathing right now contains about 25 quintillion molecules in that same space. In these cosmic nurseries, molecules like hydrogen cyanide, HCN, vibrate with a predictable frequency. First detected in the interstellar medium in 1970, HCN carries a bitter, dry scent, often compared to bitter almonds. While toxic in high concentrations, in the vacuum of space, it is a vital bridge in the formation of adenine, one of the 4 nucleobases in DNA. The universe is a slow-cooking soup of these precursors, drifting at speeds of 20 kilometers per second through the spiral arms of our galaxy. Observe the slow movement of light as it travels from distant exoplanets to our modern telescopes. In 2023, the James Webb Space Telescope turned its powerful infrared eye toward K2-18b, an exoplanet 124 light-years away. It detected traces of dimethyl sulfide, DMS. On Earth, this molecule is produced by phytoplankton in the oceans and is responsible for that briny, sea air smell we associate with the coast. Whether or not K2-18b hosts life, the presence of DMS in a world over 700 trillion miles away suggests that the scent of the sea is a chemical possibility elsewhere in the dark. Imagine the soft, bioluminescent glow of a distant alien ocean, releasing molecules that travel across the void for over a century before being caught by a mirror of gold-plated beryllium. What is happening now in your own body is a reflection of this stellar clockwork. Your cells are fueled by the breakdown of glucose, a process that mirrors the way complex carbon chains are forged in the cooling shells of red giant stars. In 1995, the Infrared Space Observatory, ISO, provided the first clear evidence that polycyclic aromatic hydrocarbons, PAH, those smoky char-like molecules, are present throughout the interstellar medium. These molecules are incredibly robust, surviving the intense radiation of the vacuum because of their stable, ring-like structures. They are the soot of the stars, the same carbon-rich material that makes up the graphite in a pencil or the charred edges of a campfire. These PAHs comprise roughly 20% of all the carbon in our galaxy, acting as a cosmic lubricant that helps clouds of gas collapse to form new suns. Grant your muscles permission to release their hold, sinking into a velvet stillness. Picture the early 20th century Russian scientist Konstantin Tsiolkovsky, who is often called the father of cosmonautics. In his early philosophical writings, he imagined a future where humans lived in ether suites among the stars. He understood even then that we are tied to our environment through the air we breathe and the scents we recognize. He envisioned a cycle where plants would purify the air of spacecraft, creating a familiar, earthy aroma in the midst of the vacuum. This vision became a reality through the veggie plant growth system on the ISS, where astronauts have successfully grown red romaine lettuce and zinnia flowers. The scent of a fresh green leaf in a metal corridor 250 miles above the Earth is a powerful sensory anchor, a reminder of the biological heritage we carry with us. As we move toward the edge of our solar system, we encounter Pluto, where the New Horizons mission in 2015 revealed a world of surprising complexity. Along the frozen plains of Sputnik Planitia, there are vast deposits of nitrogen, methane, and ammonia ice. Ammonia, NH3, which we recognize by its sharp, pungent cleaning fluid scent, is a key ingredient in the cryovolcanism of the outer planets. It acts as an antifreeze, allowing liquid water to flow like lava in the deep freezing dark of the Kuiper Belt. Imagine the silent, towering mountains of water ice, coated in a frost of nitrogen, while the faint scent of ammonia drifts through a near vacuum at temperatures of 40 Kelvin. It is a sterile, beautiful, and profoundly quiet landscape. At this very moment, the molecules that make up the scent of your home are part of a larger galactic inventory. Every time you smell a piece of fruit, a puff of smoke, or the metallic tang of a coin, you are interacting with the same chemical bonds that the Voyager probes are currently passing in the interstellar medium. The universe is not a collection of separate parts, but a single continuous flow of elements. The nitrogen in your DNA, the calcium in your teeth, and the iron in your blood were all forged in the interiors of collapsing stars. And they carry with them the olfactory history of those cataclysms. As the light of the day fades and the rhythmic pulse of the galaxy continues its slow, billion-year rotation, find comfort in the fact that your senses are tuned to the very frequency of the cosmos. The history of our discovery, from Fraunhofer's dark lines to the James Webb's detection of alien sea scents, is a story of coming home. We are learning to recognize the familiar smells of a universe that is, quite literally, our birthplace. Let the weight of this ancient knowledge settle over you like a warm, heavy quilt. The vacuum is not empty. It is a library of scents, a record of everything that has ever been, waiting for the quietest moments of the night to be remembered. Sink into the silence, supported by the physics of the bed and the chemistry of the air. As you drift further toward the heart of the great, fragrant dark. Now, as your awareness settles into the gentle rhythm of your breathing, let your mind glide toward the Perseus molecular cloud, specifically a star cluster known as Cernus 52. Within this region, located roughly 750 light-years from your bed, scientists have identified the clear spectral signature of naphthalene. On Earth, you recognize this molecule immediately as the pungent, waxy aroma of mothballs used to preserve clothes in a quiet attic or an old cedar chest. Envision this: the very chemical that guards your winter sweaters against time is drifting through the interstellar medium in vast, cold plumes. These aromatic molecules consist of two fused benzene rings, and their discovery in 2008 marked a pivotal moment in our understanding of how complex organic matter survives the journey between stars. Just as an old library carries a specific, comforting scent of aging paper and lignin, the galaxy carries naphthalene as a chemical record of its own endurance. Notice the way your body feels supported, as if gravity were a soft, invisible fabric cradling every muscle. This same gravitational force orchestrates the Space Nail Salon found in the galactic center. Within the massive star-forming region, Sagittarius B2N, astronomers in 1987 detected the presence of acetone. In your daily life, acetone is the sharp cooling liquid used as fingernail polish remover. It has the chemical formula CH3, 2CO. While the concentration in space is incredibly low, about 1 molecule for every 10 cubic meters of vacuum, the sheer volume of the cloud means there is enough acetone out there to fill Earth's oceans many times over. It is a sterile, crisp scent, evocative of a bright, clean laboratory or a fresh start. This molecule is a vital precursor to more complex chemistry, acting as a structural piece in the assembly of the life-bearing molecules that will eventually find their way into the crust of new planets. Conceive of the universe not as a void, but as a celestial confectionery. Deep within the gas cloud IRAS 16293-2422, which surrounds a pair of sun-like stars under construction, researchers using the ALMA telescope array in 2012 discovered glycolaldehyde. This is a simple sugar, a fundamental building block of RNA, if you could sense it. It would carry the faint, sweet aroma of powdered sugar or the scent in the air of a bakery just before dawn. Glycolaldehyde, C2H4O2, is a prebiotic molecule, meaning it is one step away from the chemistry of life. It exists in these cold regions where the temperature is a mere 10 Kelvin, clinging to the surfaces of tiny dust grains, like frost on a window pane. This sugar doesn't just represent sweetness, it represents the potential for complexity, the universe's way of preparing the ingredients for a future biosphere. As you continue to relax, contrast the sweetness of the sugar clouds with the intense, battery acid atmosphere of Venus. Our neighbor planet is often called Earth's twin, but its olfactory profile is entirely alien. The Venusian atmosphere is 96.5% carbon dioxide, but its clouds are composed of droplets of sulfuric acid, H2SO4. This creates a scent similar to the acrid metallic tang of a car battery or the sharp odor of a match being struck. In 2020, a team of researchers announced the detection of phosphine, pH3, in the Venusian clouds at a concentration of about 20 parts per billion. Phosphine has a scent often described as decaying fish or garlic. While the presence of phosphine remains a subject of intense scientific debate, the chemical reality of Venus is one of heavy, corrosive scents, a world that feels as dense and pressurized as the deep ocean, where the air itself has a thick, tangible weight. Observe the slow, majestic rotation of the Horsehead Nebula in the constellation of Orion. To the eye, it looks like a dark silhouette against a curtain of red light, but to a chemist, it is a dense collection of hydrocarbons. The density of the Horsehead is roughly 10,000 particles per cubic centimeter. While this is a dense nebula, it is still a better vacuum than anything we can create in a lab on Earth, where air contains 10 to the 19th power particles in every cubic centimeter. The molecules here, such as the C3H plus ion detected in 2012, contribute to a scent profile that mirrors the soot from a beeswax candle or the carbon-rich smoke of a fireplace. This smoky nebula is an active workshop where the pressure of starlight from the nearby star, Sigma Orionis, is literally eroding the cloud, stripping away layers of gas and releasing these aromatic scents into the surrounding void. Consider the buckyball, a remarkable molecule discovered in space by the Spitzer Space Telescope in 2010. Formerly known as carbon-60 or Buckminster fullerene, these are 60 carbon atoms arranged in a hollow sphere, exactly like a microscopic soccer ball. On Earth, fullerenes are found in the soot of a candle or the charred remains of a lightning strike. They carry the scent of deep ink, printer's toner, or the dry, earthy aroma of a charcoal drawing. These spheres are incredibly stable, capable of bouncing off other molecules without breaking, much like a rubber ball. They are the ball bearings of the interstellar medium, protecting other, more fragile molecules from the harsh ultraviolet radiation of young stars. As you rest, imagine these perfect carbon spheres drifting in the billions through the dark, providing a structural foundation for the galaxy's chemistry. What's happening now in the W3OH molecular cloud is even more staggering. This region, located about 6,000 light-years away, contains a vast reservoir of methanol, or wood alcohol. Scientists have measured this reservoir and found it contains roughly 100 billion liters of the substance. Methanol has a chemical scent that is slightly sweet but chemically sharp, much like the alcohol used in camp stoves. It is a key player in the formation of MASERS, microwave amplification by stimulated emission of radiation. Essentially, these methanol clouds act like giant cosmic lasers, beaming out intense microwave energy as they are excited by the heat of nearby infant stars. It is a rhythmic, energetic process, yet it happens in the silent, freezing reaches of space, where the only movement is the slow, gravitational collapse of gas into new suns. At this very moment, conceive of the Red Rectangle Nebula, a strikingly geometric cloud of dust and gas surrounding the star HD 44,179. In 1975, this nebula was found to be rich in silicates, essentially the same minerals that make up sand and glass on Earth. If you were to travel through this region, the scent would be that of warm, dry sand on a summer afternoon, or the smell of a dusty gravel road after a long, dry spell. Silicon monoxide, SiO, is common here, and it represents the bridge between the gaseous state of a dying star and the solid ground of a future rocky planet. You are, in a very real sense, a descendant of this cosmic dust. The silicon in your electronics and the oxygen in your lungs were once part of a similar sand-scented nebula, drifting through the darkness before gravity pulled them together. Notice how the rhythmic pulse of the cosmos is reflected in the seasonal changes on Mars. The Curiosity rover has spent years measuring the methane, CH4, levels in Gale Crater, noting that they fluctuate between 0.24 and 0.65 parts per billion, depending on the time of year. Methane is the primary component of natural gas, and on Earth, it is often associated with biological activity and the scent of damp, marshy soil. On Mars, this seasonal burp of methane remains a mystery, but it gives the planet a chemical heartbeat. The scent would be faint, almost undetectable, but it suggests a world that is not entirely dead, a world where the soil breathes, however slightly, beneath its rusted surface. In the deep atmosphere of Uranus, the scent profile shifts back to something more pungent. In 2018, the Gemini North Telescope confirmed that the clouds of Uranus are composed largely of hydrogen sulfide, H2S. This molecule is famous for its rotten egg odor. On Uranus, this gas exists at pressures between 1.2 and 3 bars, far above the planet's interior ice layers. While we might find the scent off-putting, it serves a vital atmospheric function, helping to regulate the planet's extreme internal heat. Below these sulfurous clouds, the pressure is so great that it forces methane into a liquid state, creating an ocean that may be thousands of miles deep. It is a world of incredible quiet pressure, where the chemistry of the air is a dense, protective shield against the cold of the outer solar system. Envision the Orion Nebula once more, but this time, focus on the sulfur dioxide, SO2, detected there. This is the same gas that creates the sharp, stinging smell of a volcanic eruption or a bleached hallway. In the vacuum, however, it is a signpost for star formation. When a massive star is born, its radiation blasts the surrounding ice-covered dust grains, vaporizing the sulfur and releasing it into the gas phase. This creates a hot core, a region of intense chemical activity that smells of the very forge of creation. These hot cores are the laboratories of the universe, where the simple atoms of the Big Bang are cooked into the complex molecules of the modern age. As you sink further into the stillness of your environment, realize that these cosmic scents are not just curiosities. They are your heritage. The formic acid, HCOOH, found in the TMC, one molecular cloud, is the same chemical that provides the sting of an ant bite or the sharp tang of a nettle. The methyl cyanide, CH3CN, found in the hearts of comets is a molecule that helps bridge the gap between simple gases and complex proteins. Every scent you have ever known, from the sweetness of sugar to the bite of wood alcohol, is a terrestrial echo of a celestial reality. The universe is a vast aromatic archive, and you are currently resting in one of its most comfortable, familiar rooms. The slow movement of light, the rhythmic orbiting of planets, and the silent vibration of molecules all work together to maintain the balance of your world. You are part of this clockwork, a breathing participant in the galaxy's long, fragrant history. Sleep now, knowing that the same physics that governs the sugar clouds of IRAS 16293-2422 is watching over the quiet, chemical peace of your own rest. As you lie there, the weight of your body pressing softly into the mattress, recognize that you are not merely a spectator of the universe, but an active participant in its chemical legacy. This connection is not abstract. It is as tangible as the air you draw into your lungs. Consider the mission of the Hayabusa 2 spacecraft, which in December 2020 returned samples from the asteroid Ryugu. Inside those precious grains of dust, scientists identified uracil, one of the 4 nucleobases in RNA, along with niacin, or vitamin B3. This means that the vitamins helping your body process energy at this very second were forged in the cold, dark reaches of an asteroid belt billions of years ago. When you sense the faint, earthy aroma of a multivitamin or the crisp scent of fresh water, you are interacting with a chemical lineage that predates the very existence of the Earth. The story of your own hydration is equally ancient. Modern research suggests that between 30% and 50% of the water on our planet, the water that makes up roughly 60% of your body, is actually older than the sun. This heavy water, or deuterium oxide, was formed in the interstellar medium under conditions of extreme cold. Picture this: the water you drank today, which now flows through your veins and helps regulate your temperature as you rest, once drifted as ice crystals in a cloud of gas long before the solar system was born. This ancient water carries no scent itself, but it acts as the universal solvent for every aroma you have ever known. It is the silent carrier of the universe's history, a liquid bridge between the birth of stars and the quiet rhythm of your pulse. At this very moment, your body is performing a sophisticated dance of molecular recognition. Within your olfactory epithelium, there are roughly 6 million sensory neurons, each equipped with receptors that can detect a staggering variety of shapes. Think of these receptors as tiny locks and the aromatic molecules from the cosmos as keys. When you perceive the scent of a lemon, you are detecting limonene, C10H16. When you smell the C, you are sensing dimethyl sulfide. This biological equipment is so sensitive that it can distinguish between 2 molecules that are identical in every way, except for being mirror images of each other, a property known as chirality. In 2016, the Rosetta mission discovered that Comet 67P contained a wide array of these chiral molecules. This discovery suggests that the handedness of life, the reason your body uses certain molecular orientations and not others, might have been decided in the frozen heart of a comet trillions of miles away. Deep within the galactic center, in the vast molecular cloud, Sagittarius B2, astronomers recently made a noteworthy discovery. In 2022, using the ALMA telescope, they identified propanol in 2 different forms, propan-1-ol and propan-2-ol. On Earth, propan-2-ol is the primary ingredient in rubbing alcohol, carrying that sharp, medicinal, and cooling scent we associate with a doctor's office or a clean workspace. The presence of these 2 isomers in space is a significant clue to the cosmic loom of chemistry. It shows that the universe is capable of weaving increasingly complex threads or molecules, moving from simple chains to branched structures. These branches are essential for the formation of amino acids and proteins. As you settle into your blankets, imagine the vast cooling plumes of alcohol vapor drifting through the galaxy, a sterile and quiet mist that serves as the laboratory for the proteins currently repairing your tissues while you sleep. What is happening now on the Moon? Enceladus, orbiting Saturn, brings this chemical connection even closer to the possibility of life. In 2023, the James Webb Space Telescope observed a massive plume of water vapor erupting from Enceladus's southern pole, stretching over 6,000 miles, nearly the distance from New York to Tokyo. Within these plumes, scientists have detected hydrogen cyanide, HCN. While we associate this with a bitter almond scent and extreme toxicity, in the context of astrobiology, it is a vital seed. Hydrogen cyanide is a primary precursor for the synthesis of adenine, a component of your DNA. Picture those towering geysers of ice and gas, smelling of almonds and sea salt, spraying the building blocks of life into the vacuum. The same molecules that define your genetic identity are currently being exhaled by a moon 1 billion miles away. Notice how the air in your room feels cool against your skin. This simple sensation of temperature is a microscopic reflection of the kinetic energy of molecules. In the interstellar medium, where temperatures can drop to 10 Kelvin, just 10 degrees above absolute zero, molecules like benzonitrile, C6H5CN, move with incredible slowness. Benzonitrile was discovered in the Taurus molecular cloud, TMC1, in 2018, and it carries a potent sweet aroma similar to almonds or cherry pits. Because of the extreme cold, these molecules don't fly apart. They huddle together on the surfaces of dust grains, forming complex ice mantles. This is the universe's way of preserving its recipes. When a new star begins to glow, its warmth thaws these ices, releasing the scents of cherries and almonds into the newly forming planetary system. You are the result of such a thaw, a collection of thawed cosmic ices, now warm and resting in the dark. Consider the bigger picture of our search for life beyond our world. We are no longer just looking for visual signs of life. We are looking for its breath. On Earth, life produces a distinct olfactory signature. For example, the scent of a pine forest is created by alpha-pinene and beta-pinene. These are volatile organic compounds, VOCs, that trees release into the atmosphere. Scientists are now developing models to detect these same VOCs in the atmospheres of exoplanets. If we were to find a planet 30 light-years away with a high concentration of pinenes, we would know that somewhere in that distant dark, there is something like a forest, breathing and scenting the air. This connection reminds us that life is not a local phenomenon. It is a chemical possibility written into the laws of physics. In 2013, researchers identified methyl acetate, CH3COOCH3, in the Orion Nebula, a region of intense starbirth. Methyl acetate has a pleasant fruity smell, often compared to pears or glue. This molecule is a structural isomer of propionic acid. The fact that the universe prefers the fruity scent of methyl acetate over the more sour acid form tells us something about the path of least resistance in cosmic chemistry. The universe often chooses the most stable, most energetic configurations. As you allow your mind to grow quiet, think of your own life in this way, as a path of least resistance toward rest, toward the most stable and restorative state of being. You are following the same physical laws that prefer the scent of pears to the sting of acid. What's happening now in your own brain is a silent symphony of these same elements. Your neurons communicate using neurotransmitters, many of which are simple organic molecules. For instance, glutamate, the most abundant neurotransmitter in your brain, is an amino acid. In 1997, acetic acid, CH3COOH, the molecule that gives vinegar its sharp, pungent scent, was found in Sagittarius B2. While vinegar might seem mundane, acetic acid is a key step in the formation of glycine, the simplest amino acid used by your nervous system to inhibit or calm neural activity. Every time you feel a wave of relaxation move through your body, you are experiencing the biological result of chemistry that is being mirrored in the heart of the galaxy. Imagine the atmosphere of the early Earth, roughly 4 billion years ago. It didn't smell like the air you breathe now. There was no oxygen, so there was no ozone. Instead, the air was thick with the scent of methane, ammonia, and volcanic sulfur. It was a heavy, pungent world. Yet in that primordial soup, the first complex molecules began to replicate. In September 2023, the OSIRIS-REx mission returned from the asteroid Bennu, bringing back samples that are incredibly rich in carbon and water. These samples represent the starting material for the Earth. They remind us that the familiar scents we love today, the smell of rain, the aroma of blooming flowers, the scent of a clean breeze, are late additions to a very long story. We are the inheritors of a transformed world, where the harsh chemicals of the early solar system have been refined into the delicate sense of life. Observe the slow movement of time as it applies to a single molecule of vinyl alcohol, CH2CHOOH, detected in space in 2001. This molecule is extremely unstable on Earth, quickly changing into acetaldehyde, which smells like green apples. However, in the low-density environment of a molecular cloud, vinyl alcohol can persist for millions of years. It exists in a state of frozen time, a chemical ghost that only changes when it finally falls into the gravity well of a planet. Your rest tonight is a similar suspension of time. For a few hours, the demands of the world are paused, and you exist in a state of quiet persistence, just like the vinyl alcohol in the void. The universe is a vast interconnected web where the scent of a green apple, the sting of rubbing alcohol, and the sweetness of a cherry are all signposts on a journey that spans billions of years and trillions of miles. You are the destination of that journey. Every element in your body, every molecule that triggers a memory of home, has been through the fire of a star and the cold of a nebula. As you move closer to sleep, feel the profound comfort of this connection. You are not a stranger in the universe. You are its most complex expression. The same gravity that holds the rings of Saturn in their rhythmic orbit is holding you safely in your bed. The same chemistry that perfumes the Orion Nebula is at work in your dreams. The void is not empty, and it is not cold. It is a familiar, fragrant, and supportive home. Sleep now, held by the ancient and enduring laws of the chemical cosmos. As you continue to settle into this state of profound stillness, imagine the very color of the universe itself. In 2002, astronomers at Johns Hopkins University averaged the light from over 200,000 galaxies to determine the average hue of the cosmos. They named this color cosmic latte, a creamy off-white shade with the hexadecimal value FFF8E7. Picture this soft, warm glow filling the space behind your closed eyes, a gentle light that represents the collective radiance of every star that has ever existed. It is the color of a quiet morning, a visual manifestation of the universe's steady, rhythmic output of energy. Scientific inquiry reveals that the why behind these cosmic scents often lies in the way molecules interact with light and temperature in the absence of an atmosphere. Consider the molecule acetaldehyde, CH3CHO, which was first detected in the massive star-forming region, Sagittarius B2, in 1971. On Earth, this compound is responsible for the crisp, slightly tart aroma of green apples. Deep within the cooling gas of a molecular cloud, Acetaldehyde forms through complex grain surface chemistry, where atoms of carbon, hydrogen, and oxygen slowly bond on the icy surfaces of dust particles. These dust grains are tiny, often less than a micrometer in size, smaller than a single human hair, yet they act as the kitchen counters of the galaxy. Within these silent nurseries, the scent of green apples is preserved in a state of deep freeze at temperatures as low as 10 Kelvin. Observe the way your hearing has begun to focus on the soft sounds of your environment. In space, sound cannot travel through a vacuum, but every planet with an atmosphere has its own unique acoustic signature. On Mars, the speed of sound is roughly 240 meters per second, significantly slower than the 340 meters per second on Earth. Because the Martian atmosphere is 95% carbon dioxide and much thinner than our own, high-pitched sounds are absorbed much faster than low-pitched ones. If you were standing on the red sands of the Jezero crater, the sound of a distant wind would lose its sharp edges, becoming a muffled, bass-heavy hum. This creates a natural, low-pass filter on the world, a soothing, muted environment where the sharp cracks of the universe are softened into a rhythmic, distant rumble. What's happening now in the protoplanetary disk surrounding the young star IRS-48 is a singular event in chemical history. In 2022, using the ALMA array in Chile, scientists discovered dimethyl ether, CH3OCH3, the largest molecule ever identified in a planet-forming disk. Dimethyl ether is a colorless gas that, on Earth, has a faint, ethereal, and slightly sweet scent, often used as a refrigerant. Its presence in a disk, 444 light-years away, tells us that complex aromatic molecules are present even before planets are fully formed. Imagine the texture of this region, a swirling, grainy soup of ice and gas, where the molecules that will one day form a planet's atmosphere are already colliding with the grace of slow-motion snowflakes. This is the universe as a silent chemical weaver, braiding together the simple threads of hydrogen and carbon into the intricate tapestry of a future world. Surrender your focus to the strange and beautiful textures of Saturn's moon, Titan. Unlike the silicate sand of Earth's deserts, the vast dunes of Titan, which can reach heights of over 300 feet, are composed of organic hydrocarbon grains. These grains have a texture similar to coffee grounds or fine soot. They are created in the upper atmosphere when sunlight breaks down methane and nitrogen, which then rain down as a fine, dark powder. Titan is a world of soft landings, where the gravity is only about 14% of Earth's. Walking through these hydrocarbon dunes would feel like moving through a dream, a dark, silent landscape that smells of propene, C3H4, a molecule detected by the Cassini mission that carries a scent similar to a cold, metallic tang. Notice how the thermal conductivity of a vacuum is essentially zero, making space the most perfect insulator in existence. This is why a thermos works so well. It uses a vacuum to prevent heat from escaping. As you lie in the warmth of your room, envision the 2.725 Kelvin temperature of the cosmic microwave background, CMB, the afterglow of the Big Bang. This faint heat permeates every cubic centimeter of the universe. It is a constant, steady warmth that has been cooling for 13.8 billion years. This temperature is a fundamental floor of the universe's energy, a baseline of calm that ensures the void is never truly at absolute zero. You are resting on a thermal foundation that has been stabilizing since the dawn of time. At this very moment, consider the singular ridge on Saturn's moon Iapetus. This mountain range spans half the moon's circumference and reaches heights of 13 miles, nearly double the height of Mount Everest. Scientists discovered this walnut-like feature in 2004, and its origin remains a subject of curiosity. It may be the remains of a collapsed ring system that once orbited the moon. The texture of Iapetus is a stark contrast of bright white water ice and dark, carbonaceous material that smells of wood smoke. As the moon slowly rotates every 79 days, the transition from light to dark is a slow-motion dance of temperatures, a rhythmic shift that has persisted for billions of years without interruption. Scientific inquiry into the origins of life often points toward formamide, NH2CHO. This molecule has been detected in numerous comets and in the dense gas of the interstellar medium. Formamide has a very faint, almost undetectable scent of ammonia, but its importance is immense. It is a multi-purpose molecule that can lead to the formation of sugars, amino acids, and nucleic acids. In 2014, the Rosetta mission confirmed its presence on Comet 67P. Picture these prebiotic molecules as the silent seeds of the universe, drifting in the cold, waiting for a warm, watery environment to begin the process of unfolding. The universe is not a sterile graveyard. It is a grand cold storage library, preserving the blueprints for life in a state of aromatic suspension. Enable your mind to visualize the sodium tail of Mercury. This planet, the closest to our sun, has a comet-like tail made of sodium atoms blasted off its surface by the solar wind. This tail can stretch over 15 million miles behind the planet. Sodium is the primary component of sea salt, NaCl, and though the tail is too thin to smell, it represents a constant rhythmic shedding of the planet's skin. Mercury is a world of extreme sensory contrasts. On its day side, temperatures soar to 800 degrees Fahrenheit, while the night side plunges to minus 290 degrees. Yet, even in this harsh environment, there is water ice hidden in the permanent shadows of its polar craters, a cool, frozen secret kept in a world of fire. There is a profound logic to the presence of carbon monoxide, CO, in the interstellar medium. It is the second most abundant molecule in the universe, following only molecular hydrogen, H2. While toxic to us on Earth, in space, carbon monoxide is the primary tool astronomers use to map the galaxy. Because H2 is hard to detect, the rhythmic glow of CO as it vibrates and rotates provides the map of where new stars are being born. Carbon monoxide has no scent, but it is the silent lighthouse of the cosmos, guiding us toward the regions where the scents of the future, the raspberries, the almonds, and the green apples, are currently being manufactured. Deep within the gas giant Jupiter, the pressure is estimated to reach 70 million bars, 70 million times the atmospheric pressure you are feeling right now. At these depths, hydrogen is squeezed until it becomes a liquid metal. This metallic hydrogen creates a massive magnetic field that shields the moons of Jupiter from solar radiation. It is a world of immense quiet power, where the chemistry of the interior is hidden beneath thousands of miles of colorful clouds. These clouds are striped with bands of ammonium hydrosulfide and ammonia ice, creating a scent profile of sharp cleaning fluid mixed with the earthy smell of a damp basement. Despite the internal pressure, the outer layers of Jupiter follow a predictable rhythmic rotation, completing a day in just 9 hours and 56 minutes. Scientists discovered in 2015 that Pluto's moon, Charon, has a red pole, a region of dark reddish-brown material named Mordor macula. This color is caused by tholins, complex organic molecules created when ultraviolet light hits methane. These tholins have a gritty, plastic-like texture and a scent reminiscent of asphalt or burnt toast. Furthermore, Charon has been found to have patches of ammonia ice, NH3, on its surface, as confirmed by the New Horizons spacecraft. This suggests that the Moon may have had internal cryovolcanoes in its past, spraying a mixture of water and ammonia into the near vacuum of the Kuiper Belt. Imagine the silent, frozen landscape of Charon, where the air is 1 trillion times thinner than Earth's, and the only movement is the slow, distant orbit of Pluto, just 12,000 miles away. As you prepare to transition into the final phase of your journey, permit your consciousness to drift toward the molecule methanamine, CH2NH, detected in Sagittarius B2. This molecule is a crucial precursor to glycine, the simplest amino acid used in your body to build muscle and send signals between neurons. Methanamine carries a sharp, pungent aroma, yet it is a stepping stone toward the biological peace of your own rest. The universe operates on these long, slow timescales, where a molecule can drift for 1 million years before it finds its purpose. You are currently experiencing the biological reward of these cosmic cycles. Your heart rate is slowing to match the rhythmic pulse of a distant pulsar. Your body temperature is stabilizing like the cooling crust of a young planet. The cosmic latte of the universe's light is fading into the comforting dark of your room. Every scent and texture we have explored, from the coffee-ground dunes of Titan to the salt tail of Mercury, is a part of the grand logical clockwork that has brought you to this moment of safety. There is no urgency in the stars, only the slow, beautiful dance of gravity and the silent, aromatic persistence of the void. You are a part of this logic, a calm and resting node in a vast, fragrant network of light and matter. As the slow, rhythmic tides of the galaxy carry us toward the end of our journey, let us observe the gradual, step-by-step unfolding of how a single familiar scent comes to be. From the heart of a star to the quiet room where you now rest. At this very moment, your body is a vessel for elements that have traveled across billions of years, following a logical and beautiful process of assembly. This process begins deep within the core of a dying star, where the temperature reaches a staggering 100 million Kelvin. Here, through a mechanism known as the triple alpha process, 3 helium nuclei fuse together to form a single atom of carbon. This carbon is the fundamental backbone of every aromatic molecule you have ever perceived, from the sweetness of a raspberry to the smoky char of a campfire. The next step in this grand unfolding occurs as the star reaches the end of its life cycle, gently shedding its outer layers into the surrounding void. This material is ejected at speeds ranging from 10 to 20 kilometers per second, cooling as it expands into the interstellar medium. Within these cooling plumes, carbon atoms begin to link together, forming complex structures called polycyclic aromatic hydrocarbons, or PAHs. Scientists discovered that these molecules, which carry a distinct smoky scent, account for roughly 10% to 20% of all the carbon in our galaxy. Notice how this vast chemical dispersal is a silent, graceful expansion, a slow-motion breath exhaled by a star that serves to enrich the entire neighborhood of space with the ingredients for future worlds. As these carbon-rich particles drift through the cold, dark regions of molecular clouds, they encounter temperatures as low as 10 Kelvin. At these extremes, a fascinating process called quantum tunneling allows chemical reactions to occur that would otherwise be impossible in such cold. Hydrogen atoms literally tunnel through energy barriers to bond with carbon and oxygen on the surfaces of microscopic dust grains. Over millions of years, these dust grains become coated in ice mantles made of water, ammonia, and methanol. This is the universe's method of preservation, a slow, frosty accumulation that builds a library of complex organic molecules, including the precursors to the amino acids that make up your very being. Consider the subsequent stage, the formation of a solar system. Roughly 4.6 billion years ago, a shockwave from a nearby supernova triggered the collapse of such a cloud, forming our sun and a swirling disk of debris. Within this disk, a process called accretion began. Small grains of dust collided and stuck together, growing into planetesimals and eventually into the planets we know today. During this era, between 3.8 and 4.1 billion years ago, a period known as the Late Heavy Bombardment occurred. During this time, a massive number of comets and asteroids impacted the young Earth. These icy messengers were not just bringers of destruction. They were the delivery system for life's aromatic ingredients. In 2004, NASA's Stardust mission flew through the coma of Comet 81P/Wild 2 and captured dust samples that were returned to Earth 2 years later. Inside these samples, scientists identified the amino acid glycine, NH2CH2COOH. Glycine has no strong scent itself, but it is the simplest amino acid used by all living organisms to build proteins. The fact that glycine can be found in the frozen heart of a comet proves that the chemistry of your own muscles and nerves was organized in the silent, cold forge of the outer solar system. You are a biological extension of this cometary delivery, a gradual assembly of ancient interstellar parts. As the Earth stabilized, its atmosphere underwent a monumental transformation. Around 2.4 billion years ago, a process called the Great Oxidation Event began. Cyanobacteria in the oceans started producing oxygen as a byproduct of photosynthesis. This oxygen eventually rose into the upper atmosphere, where ultraviolet radiation from the sun split the O2 molecules, allowing them to reform as O3, or ozone. This is the very same ozone that astronauts smell in the airlocks of the space station today, that sharp, metallic, electric scent. This layer of ozone became a protective shield, absorbing 97% to 99% of the sun's high-frequency ultraviolet light, making the surface of the planet safe for the complex life that would one day perceive the sense of the world. Think of the way a familiar scent, like the smell of rain, after a dry spell brings you a sense of profound peace. This scent, known as petrichor, a term coined in 1964 by researchers Isabel Baer and Richard Thomas, is a specific chemical process involving the molecule geosmin, C10H18O. Geosmin is produced by Streptomyces bacteria in the soil as they go through their life cycles. When rain hits the earth, it traps tiny bubbles of air containing this molecule, which then burst and release the scent into the atmosphere as an aerosol. Human beings are incredibly sensitive to this smell, capable of detecting it at concentrations as low as 5 parts per trillion. This sensitivity is a biological anchor, a connection to the fundamental cycle of water and life on our planet. Notice the slow movement of air in your room and realize that your own physiology is currently following a rhythmic, ancient protocol for rest. As the light fades, your pineal gland, a small pea-sized gland in the brain, begins to convert the neurotransmitter serotonin into melatonin. This process is triggered by the decrease in light hitting your retinas, signaling to your body that it is time to down-regulate. Melatonin levels typically begin to rise about 2 hours before you fall asleep, peaking in the middle of the night. This is a chemical transition as predictable as the orbits of the planets, an internal clockwork that syncs you with the rotation of the Earth. Deep within your brain, while you rest, your neurons produce a specific pattern of electrical activity known as sleep spindles. These are rapid bursts of brain activity, typically ranging from 11 to 16 Hz, occurring during stage 2 non-REM sleep. These spindles are thought to be the brain's way of shielding your sleep from outside noise, ensuring that your rest remains undisturbed. While this happens, your brain's glymphatic system becomes 10 times more active than it is during the day. This system facilitates the clearing of metabolic waste, such as the protein beta amyloid, by pumping cerebrospinal fluid through the spaces between your neurons. It is a nightly purification, a rhythmic clearing of the day's chemical debris to prepare you for a fresh start. Furthermore, consider the molecule adenosine, C10H13N5O4. Throughout the day, as you move and think, adenosine builds up in your brain as a byproduct of cellular energy consumption. This sleep pressure is what makes you feel heavy and ready for rest. During the night, your body systematically breaks down and clears this adenosine, resetting the pressure. This is a perfect, step-by-step chemical balance, a biological reflection of the way stars consume their fuel and return it to the galaxy. You are currently in the middle of this restorative cycle, a quiet participant in the universe's grand economy of energy. As you drift toward the final descent into sleep, let your awareness broaden one last time to include the entire cosmos. You are made of the carbon from red giants, the iron from supernovae, and the ancient water from the interstellar medium. The familiar scents that bring you comfort, the almond of a comet, the smoky char of a star's breath, the earthy rain of our home, are the sensory proof that you belong to this system. There is no separation between the chemistry of the Orion Nebula and the chemistry of your own thoughts. You are a way for the universe to know itself, to breathe itself, and to rest within itself. The observation of the universe's clockwork is coming to a gentle, supportive halt. The stars will continue their slow dance of gravity. The planets will maintain their rhythmic orbits, and the molecules of the void will continue to vibrate in the cold. But for now, your role is simply to exist in the stillness. Feel the warmth of your own rest, an internal glow that mirrors the cosmic latte of the galaxy's light. You are safe. You are home. You are held by the laws of physics and the comfort of the familiar. Now, allow these affirmations to wash over you like a slow, cooling wave of stardust. I am a part of the universe's ancient and beautiful logic. The rhythms of the cosmos are reflected in the quiet pace of my breath. My body knows exactly how to return to a state of perfect balance. I am supported by the steady, unmoving force of gravity. Every cell in my body is at peace with the history of the stars. I am clear, I am calm, and I am resting in the heart of the void. The vastness of space is not empty, but filled with the ingredients of my dreams. I release the day's energy back to the stars, where it began. My rest is a sacred part of the galaxy's long and fragrant history. I am weighted by the comfort of the earth and the silence of the night. The atoms within me are returning to their most stable, peaceful state. I am a miracle of chemistry, a conscious spark in the great dark theater of the void. The universe is watching over my rest with the steady light of a billion suns. I am drifting into a deep, restorative, and ancient sleep. The light of the distant galaxies is dimming. The scents of the cosmos are fading into the soft, neutral air of your room. The pressure of the world has dissolved, leaving only the weightless feeling of your mind as it floats into the silence. There is nothing left to do, nothing left to observe. The process is complete. The cycle is whole. Good night.